And I'm Haruki Watanabe, University of Tokyo, and I'm actually doing condensed matter physics recently, and I think my topic I chose today is slightly unfamiliar to other participants, so I try to go very slowly and try to tell you the basic idea, not the detail, but so please interrupt me and stop me anytime if you have questions. That will help you or help other participants, and also I didn't prepare many slides, so if you interrupt me, that's really great. Okay, so I'm going to talk about boundary correspondence of topologically trivial insulators, and these works are done with my PhD student, Seishiro Ono. He's like a fourth year in PhD, and Hoi Junpo, he's a very active guy, working on many different things, and he recently became a PI in Hong Kong University of Science and Technology. Okay, so as you know, there are a variety of materials in condensed matter systems, like the number of elements are huge, and also there are many different types of crystals. Like even if we limit ourselves to crystalline type material, like there are many other things like glasses or I don't know, whatever. But today I'm going to talk about very simple things. So I want to assume like crystalline structure. So maybe given this nature of materials, I can say it's fair to say this is like a quantum mechanical systems, and also large quantum number, or at least the number of particles involved in these systems are large. So maybe this talk may fit in this overall topic, but unfortunately, the most interesting part of this story, the topic I chose today, is not really quantum or really large quantum number, but you will see what I mean later. Okay, so given this variety, we want to have some unified or systematic classification of these systems. The first thing we try is to ask whether the system spontaneously breaks symmetry. So we assume some symmetry to the system, like time reversal symmetry or translation symmetry, or say U1 symmetry or particle number conservation, or spin rotation symmetry, whatever symmetry we assume, and ask if the material or the system spontaneously breaks it. So that's the first classification. Then we ask if there are excitation gap on the top of the ground state. We know that the property of the material are completely different between if the excitation are all gapped or gapless. So that's what we want to know. Then we ask that degeneracy of the ground state. So for example, like let's imagine that we have a Hamiltonian infinite system, and let us just diagonalize it, like numerically, putting in computer. We disturb all energy levels and ask what's the ground state degeneracy and what the excitations. And these classification gives us useful classification. Like, for example, if the system breaks continuous symmetry, then the state becomes okay. So this phase with continuous symmetry breaking contains Goldstone modes. So that's the topic I studied for my first research project as a PhD student. And there are many other phases like long-range entangled phases, and this contains fractional quantum Hall state or fractal topological orders. And these are things condensed matter people are recently working on very actively. Also, this short-range entangled phases contains, of course, trivial phases, but also topologically non-trivial phases. And this classification is subtle, like you compare the number of degeneracy, and the distinction between two phases is the following. So symmetry breaking implies degeneracy in the ground state, right? So usually the number of degeneracy is given by this, the dimension of concept space G over H. So usually this explains the complete degeneracy. But if you have more degeneracy than you might expect from spontaneous symmetry breaking, then your phase is long-range entangled. Otherwise, it is short-range entangled. So this contains no symmetry breaking case and no degeneracy case, or some symmetry breaking case, but the degeneracy is more than the broken, more than you expect from symmetry pattern of symmetry breaking. So when I started my PhD research, I was first interested in number Gaussian modes in continuous symmetry breaking phases. And I asked, how many Gaussian modes appear given spontaneous symmetry breaking pattern, like, say your Hamiltonian contains Lie group G that spontaneously broken into its subgroup H. Then, in relativistic field theory, we know that we expect the number of Gaussian modes we obtain as a result of this symmetry breaking is given by the number of broken generators, and that is given by the other dimension of the coset space, right? And this can be understood from writing down a log effective Lagrangian. So if this coset space is one-dimensional, we have only one direction of fluctuation. If this coset space is two-dimensional, then you have two independent directional fluctuations. So you have two Gaussian modes, and this can be understood from this kind of effective Lagrangian. So, but in condensed matter systems, you have more variety, as I said. So depending on the system, this simple rule can be broken. So in non-relativistic systems, in general, the counting rules get modified. So you have this correction term to the counting. So number of Gaussian modes you expect in general is less than or fewer than the number of broken generators. And this matrix law is given by the simple formula which we proved in this paper. So this matrix law is given by the expectation value of the commutation relation between symmetry generators. Qi and Qj are broken generators, and we take expectation value, and that gives you this law ij. You compute rank of law, and this quantity always vanishes for relativistic systems because this is zeroth component of like a for current. So this is a temporal component. So this is in general zero for Laurent invariant cases, but in non-relativistic systems, it is allowed to be non-zero. And when that happens, this matrix law becomes can be put in this form. And when the number of Gaussian modes get fewer than the number of broken generators, then you see that dispersion relation might be not linear. So if you look at the small k limit, usually the dispersion is linear, as in this relativistic case, but in condensed matter systems, it is allowed to be quadratic. And we proved this formula by writing down this kind of effective Lagrangian. So now, because of the absence of Lorentz symmetry, temporal derivative doesn't necessarily come in pairs. So single time derivative is allowed. Then, in Fourier space, this gives us Omier, and we have k squared. So this is the reason why we get this quadratic dispersion. And when this happens, then you see that this Gaussian mode pi b becomes canonical conjugate of this mode field pi a. So that's the reason why we have fewer number of independent Gaussian modes. And when this happens, the fluctuation is not really independent in two directions. They are paired up in a single precession way of fluctuation. So this is the reason why we have this variety. And I explained this because as I said, I want to have some systematic understanding of condensed matter systems. And now I explained my understanding of this continuous symmetry broken phases. At least low energy excitations, number of modes can be counted that way. But today, my focus is not in this gapless ordered phase. I want to talk about, I want to develop some systematic understanding of this short-range entangled phases. Okay. But okay, I also wanted to advertise some of my previous study for some like spontaneous symmetry breaking. So you know, when people talk about spontaneous symmetry breaking, usually people talk about translation symmetry in space or rotation symmetry in quantum systems. But Frank Wilczek in 2012 asked a very nice question about, you know, whether translation symmetry is broken or not. And quantum time crystal can be best understood by comparing it against a conventional crystal. Like one way of understanding conventional crystal is that, you know, as a function of position x, the ground state excitation value of density operator of ions or atoms in material, it oscillates in space. So this is almost a definition of crystal. And this spontaneous formation of this modulation characterized crystal. So time crystal is just you replace position x with time t and ask whether in ground state it is possible to have oscillation of expectation value of one operator. And we formulated it in terms of long-range correlation function, and we proved that it is not in general possible in ground state or in equilibrium. So, you know, we gave one definition of time crystal. So that is given by this correlation function, like a long-range correlation function characterize a coherent motion of the space. And we proved using just a locality of the Hamiltonian, or yeah, just a locality of the Hamiltonian, that, you know, this kind of correlation function doesn't depend on time. In the limit, v goes to infinity and x get far away to each other. You know, x, and you know, when for small x, this correlation function measures a local excitation of the system. So it is usually depending on time. But that's like a short range physics. Like we are interested in like long range coherent motion in space, and that is prohibited in quantum systems. So this is our proof of, you know, absence of quantum time crystal. And recently people realized that it is possible to have time crystal in non-equilibrium systems, like driven systems. For example, like if you have system and if you apply external field, like with frequency omega, then if the system responds to it with frequency 2 omega, then we say time translation symmetry, like discrete time translation symmetry, is broken to the half of the, you know, initial symmetry. So that's the, you know, discrete time crystal. So like I've been working on this kind of, you know, some general things about spontaneous symmetry breaking, but today my focus is on this, you know, phase, which is in general doesn't break symmetry, or even if it breaks symmetry, it is like a discrete symmetry, and you know, the ground state is gapped. And in addition to that, the gap of the ground state can be explained by the ground state degeneracy. So there's no like a long range entanglement. Like this is like a very simple system, but this phase still contains like topological insulators, or more generally like a symmetry protected topological phases. Yeah, is there any questions so far? Or yeah. So how do we classify short range entangled phases? So this is, you know, this phase. Okay.
Can I ask you a quick question that is actually about things you will not talk about? How is it possible to have more degeneracy than G over H? I mean,
oh yeah, so that so that's very interesting thing, right? So you to see this kind of degeneracy, you have to be careful about your spatial manifold. So like you see, you put system, say for example, on torus. In other words, you impose periodic boundary condition. Okay. Then this kind of long range entangled phases shows degeneracy depending on the geometry of the topology of the spatial manifold. Like on torus, for example, like 4-fold degeneracy. On sphere, it's 2-fold degeneracy. It depends on the like a genus or topology of the space. And that's That's really like a fascinating property of these kind of phases, and that is why it is called the long-range entangle. It's not really a product state. It's very interesting. There are many concrete examples, like fractional quantum Hall state is an example. If you know like a toric code model of some spin systems, you can really write down such kind of models, and exact ground state is known, and you can play with special manifold to see the change of the degeneracy depending on the topology of the manifold. And so these are things what the people are studying. So I agree that this is non-trivial. And when I first heard of it, I was very excited. And but unfortunately, that's not what I'm going to cover. And I recommend you to just look, Google toric code model.
Okay.
That's a very simple model, and it's very.
No. I understand you talk about something. I was just curious. It seems
yeah.
That's why.
Yeah. Thanks for asking. Yeah, I completely agree that that's non-trivial. Yeah. Okay, but I'm going to talk about a much simpler situation, like a short-range entangle phases. It can be trivial phases, or not necessarily very, very quantum. You'll see. So, so how do we classify short-range entangle phases? So, previously I tried to classify gapless phases, spontaneous symmetry breaking from symmetry breaking pattern G to H, right? Do we have such kind of systematic understanding? So, so we start from assuming some symmetry G, and as I said, we assume excitation gap delta. So this is a basic assumption of this classifying this phase, and we assume that phases we want to classify is a ground state of some Hamiltonian symmetric under G, and we ask if two Hamiltonians can be adiabatically connected to each other without breaking symmetry G or without closing gap delta. Is there a path connecting, smooth path connecting H1 to H2? Like, just, this can be one parameter family of this Hamiltonian, and T equals 0 is H1, T equals 1 becomes, say, H2. When that happens, we say two phases are the same. And given this classification scheme, we can classify all Hamiltonians symmetric under G with excitation gap delta. Then, draw some lines, like, you can these, so in this example, we have three phases. And some Hamiltonian has ground state, which is a product state. Then we say that is a trivial phase. So this is topologically trivial because it contains product state. Product state is just a linear, I have, say, for example, lattice system. I have spin up here, down here, up here, down here, or you have a particle systems with occupied state, unoccupied state, occupied state, unoccupied state, like that. It's just a completely trivial, no entanglement. That is product state. And product state is not necessarily unique. For example, spins are all up here or down here. If there's a symmetry to distinguish them, we say they are different state. So, it's not necessarily that product state is trivial state is unique. So we have many classifications, but there is some phases which doesn't contain product state. In other words, that this phase contains irremovable entanglement. So that is called topological phase. So maybe we can classify phases like this. Trivial phases are connected to Gibbs phase product states like this. And topological phases doesn't contain a trivial state in it. So that contains irremovable quantum entanglement. And that is topological phase. Now, what is interesting about this classification is that we have bulk boundary correspondence. So knowing only the bulk, so if we define system on, say, torus, which doesn't have any boundary, we know only the bulk, but we know some information about the edge of the system, boundary of the system. So if we impose open boundary condition, we can predict what happens on the edge. So that's bulk boundary correspondence. So interesting example is quantum spin Hall insulator. We have a bulk we classified with Z2 invariant, and it contains some modes that propagate along the edge. And this is the reason why we are interested and study a lot about topological insulators in last 2 decades in condensate systems. Like we want to understand the relation between bulk and edge. And there are more classic example like a Haldane phase. This is like a spin. We have spin 1. So these are spin S=1 spins defined on lattice. But somehow spin 1/2 degree of freedom emerges as an edge degree of freedom. So this is like a fractionalization of spin 1 into spin 1/2. So that is very surprising if you spin 1/2 is a say projective representation of spatial rotation, or this is very weird stuff if you start from S=1 system, but it is possible to realize such kind of degree of freedom as an edge mode. So this is another example of bulk and boundary correspondence. So the key message here is that non-trivial topology in general implies non-trivial boundary. And non-trivial boundary here, we mean it is some degree of freedom. So it is gapless, or at least the dimension of the Hilbert space on boundary is not 1. It's like we have a mode which can be excited, and we have gapless mode or 0 mode on the boundary. So these are the common feature of these topological phases. And one way of understanding this bulk boundary correspondence, I think, is like an anomaly inflow. So this is the simplest example of quantum integer quantum Hall systems. The bulk is characterized by Chern-Simon theory, like ADA. And we know that this is a gauge invariant if it doesn't contain any boundary. But if the spatial manifold contains boundary, then it is no longer the case. Like we have integration by part. The surface term doesn't vanish. So this action is not gauge invariant if the system has boundary like this. And okay, so bulk spectrum is like a random level if we start from a system with uniform magnetic field, and we occupy, say, lowest random level to realize this bulk. But as I said, this, like this geometry, this action is not gauge invariant. So such kind of gauge dependence can be compensated, cancelled by edge mode, chiral edge mode. So in this case, we have a chiral edge mode, which shows chiral anomaly. It doesn't, the number of particles in this system is not really conserved. So, 2 gauge dependence from the bulk and edge cancel perfectly, and the total number of system in this system is in this entire system is conserved. So that this is why, knowing only the bulk, we know something must happen on the edge, and knowing only the edge, we know what happened in the bulk of the system, right? So this is the bulk boundary correspondence, and this understanding is robust against say decoration or perturbation of the surface. Like you can do whatever you want to the surface, but you cannot eliminate this chiral anomaly. Like if you insert additional flux to the bulk, the number of particles must be changed. This is necessary to conserve the number of particles in the system, which we assume like if you prepare disk in condensate systems, and if you do not have any lead attached to it, then the number of particles must be conserved. We know that, and so we know such kind of understanding is robust against any decoration or perturbation we do to the system, right? And last decade or 10 years ago, like people realized that there are many more varieties to topological bulk boundary correspondence. So the example I just explained is like a 2-dimensional bulk and a 1-dimensional edge. So this is, sorry, like this is condensate terminology, but I don't include type direction in counting the dimension. So this is 2-dimensional space. But there is an example in which for 2-dimensional space, 2 spatial direction, 2 spatial dimension, 0 mode appeared, but the 0 mode doesn't live in the edge, but it lives on corners. So this is called like a higher order topological state. Like this is second order state. So in three spatial dimensions, surface can be gapped, but hinges are gapless, or corners are gapless, or corners contain zero mode. So this is possible, and this is called third order topology. And people looked for material example of these phases, and they really found it like this mass is turned out to be high order topological insulator. Anyway, the key message here is that boundary state can be localized to corners of hinges, depending on the bulk topology. So bulk topology implies various type of surface states. It can be gapless Dirac mode on surface, or hinge state, or zero mode on corners. Okay. Any questions? Good. So I also wanted to advertise some of my work. These are slightly off topic, but this is called like Symmetry Integers. And I'm explaining this because there's like a kind of paradigm shift. Yeah.
Can I ask you about the thing of before? So you say that you can have gapless modes, either localized on points or on lines or surfaces. Yeah. But is this fixed in the sense that if I have a given bulk theory, can it be that I have localized boundary modes of different kinds, or this is just fixed given the bulk theory? You see what I mean?
Yeah. So okay. So of course, like we want to talk about only that like which can be predicted from the bulk. So like if you yeah. So let me explain what I mean. So here, like I showed you like chiral mode, but in general, if you really diagonalize Hamiltonian in condensed systems, there are a bunch of gapped mode, right? They are higher in energy, so we neglect them because they are not robust, or they are not universal. But maybe you can just put them in lower energy and make it gapless if you part of your system, right? But that's not universal. It's not protected by any symmetry. So I don't include them in this discussion. So what I'm saying is that if we limit ourselves to only universal part of the edge, or surface mode, then the correspondence is almost unique. Like for this bulk, the only possibility is to have this chiral edge mode, and like in this system, if you only look at those protected by symmetry, then in this example, surface is gapped, but we have only one chiral edge mode. So this is like in this example, I start from three-dimensional topological insulator and simply apply magnetic field. And in this case, if we require inversion symmetry, but only inversion symmetry, then because I don't assume time reversal symmetry, surface can be gapped. But we know in this case that there is a remaining 1D chiral mode. This is protected by inversion symmetry. So if you break inversion symmetry, I can remove it. But under the assumption of inversion symmetry, there's no way to unwind this loop from the surface. So in that way, like as long as you allow for perturbation that is allowed by symmetry, then the surface feature is almost unique.
But for example, in that case, couldn't I have, instead of that mode, something localized on the two poles? Wouldn't that also satisfy the symmetry?
So
exactly, to localize in 2 points on the two poles.
Yeah. So what do you want to localize there? Like a zero mode or something? Yeah. Okay. Good. Yeah. So like in this case, I know that is not possible because so okay. So in this case, I know that the bulk topology implies that the system must show second order topology. So I know some line hinges or some lines that so there is a one-dimensional gapless mode on the surface. So zero-dimensional zero mode on the poles is not sufficient. So that's like okay. So maybe we need to do this kind of understanding. What is necessary from the bulk perspective on the surface. But I'm just explaining the results. So sorry, like
No. It's okay. I was just
I
was thinking of the example of before, and I was wondering if you can compensate for
So,
the anomaly in different ways. That's
right. That's right. Yeah. So there are the bulk topology must be so in such that this surface can be gapped to realize the kind of zero-dimensional zero mode. So these are all depends on the bulk topology. So condenser people try to bridge bulk classification and surface classification. So I hope what we are doing is not only try to study many different things. Like I just wanted to tell you that the condenser people are doing something systematic and try to study the variety. And there are nice I don't know, very complicated classifications of try to understand what kind of boundary is allowed for each bulk topology. So yeah, we need to look up these references to fully answer to your question. But I hope that was enough. Yeah.
No, I think I understand. Thank you.
Good. Yeah, thanks. Okay, so this was bulk boundary correspondence of higher topological insulators. And I was about to say that recently there was a paradigm shift in material search in condensed matter physics. Like for given material, studying topology of the material is very hard. In general, very hard. You have to find a wave function of the ground state and compute some winding number. So that's very hard. But there's a way of doing the calculation very simply. So this is called like a symmetry indicator. Like I just show you some simple example. Like so this I'm imagining spins. This spin can point in XY direction, like in plane direction. So this is direction of the spin is S1, and my spatial geometry is also S1. So I have a spins on ring, right? In this case, the topology I want to classify will be just a winding number, right? So in this example, I have winding number 1 and winding number 2 here. But suppose that I don't have a wave function of the entire space. Suppose that I know only spins on some axis. So let me assume some additional symmetry to the system, which is rotation symmetry about this axis. Then spins on this axis is quantized to either pointing right or left, right? It cannot point to up or down because of this C2 symmetry. So then just by comparing the direction of these two spins, I can tell the parity of the winding number. If they are in the opposite direction, the parity is winding number is odd. If they are in the same direction, the parity is even. So this simple analysis of just looking at high symmetry points and look at the eigenvalue or representation of the symmetry, this really helps in diagnosing topology of the material. So in band structure, so this is band structure, this is momentum space, and in general, this is very complicated. But we don't have to look at the entire momentum space. We look at only high symmetry points and the representation of symmetry. That already gives us very, that's already very informative to tell us topology. And people looked at material on database and computed topology using this scheme, and people found thousands of new materials from this kind of simple calculations. So like instead of one-by-one calculation of using 4 wave functions computed from first principle calculations, now people looked at material database and computed only the symmetry representations at high symmetry points to compute topology of the material and discover many topological insulators, or topological non-trivial materials. So that's what people are doing in condenser systems. Yeah, but now let me change the topic slightly to bulk boundary correspondence of topological trivial insulators. So I define trivial insulators to be almost unique ground state, which contains which can be smoothly connected to product state, right? So this might be very just trivial, but still people found that it can still have some kind of topological signature. So this is the real space diagram, and this vertical axis is charge density of the system. So if you integrate charges localized to the corner, you see some fraction of charges, like this in this case it is quantized to the integer multiple of a quarter of unit charge E, or this in this case it is half of unit charge. So we have many insulators like this. Fractional charges are localized to corners. And I heard of this story, and I wanted to ask, what is the relation between bulk topology or bulk signature and the charge localized to the corner? Can we have systematic understanding of this? So that is the topic of today's talk. And we know, this happens many times in actually we have a classical example that is polarization and edge charge. So in the electromagnetism in not graduate school, I think in undergrad in electromagnetism, we learned that for a given charge distribution, we can compute polarization. So polarization in this case is computed for this kind of point charge. We can compute it using charge multiplied by a coordinate. So this gives you some number, like in this case it is E d over A. So A is a unit length of the unit cell, lattice constant. Then like this polarization P is non-zero in the bulk, and it becomes zero in the vacuum, right? So this kind of change of the polarization implies the appearance of charges localized to the edge of the system. So this is one example of bulk boundary correspondence of trivial insulators, which is characterized by polarization. And maybe I think high energy people are familiar with this kind of story from this example, like solitons in polyacetylene. So polyacetylene is this kind of material, like carbon atoms are connected by single bond or double bond, and the position of the double bond is either this side or that side. And we have two types of single double bond alternation, and the domain wall we can have some domain wall in between, right? And people realize that this domain wall contains fractional charge. So in this case, the charge unit is actually 2e, because we are talking about this kind of bond, right? This bonding is usually charge unit is 2e. So each bond contains charge 2e, but this solitons in polyacetylene contains fractional charge, fractional in this 2e sense. This is charged with e, which is half of 2e. So this we say this is fractional charge. And so I think this is a very this example is very similar to this one, like polarization. So polarization changes here. So that is why we have localized charge. So what we want to investigate is this type of story, but for a three-dimensional crystal, and fractional charge appears at corner. And people developed several theory to describe this kind of polarization. So because we want to understand boundary or edge without explicitly computing the boundary, but just looking at bulk. So we first assume periodic boundary condition and compute something like a Berry phase or some topological number. Then we predict what kind of charges we expect if we impose open boundary condition. So that's like a bulk boundary correspondence. Or this kind of theory is called modern theory of polarization. We say this is modern theory because the formula I explained this is really classical. This is classical E&M, and it doesn't really work for quantum systems. So there are like 30 years ago, people developed formulas like Berry phase formulas that works for quantum systems to predict corner edge charge. And there's a formula for bound insulators and also formula for interacting systems. And so I want to say we know how to compute polarization of the bulk in quantum systems in the bulk that predicts charges appearing at edges of the system. Then can we do the same thing for higher order multiples, like not necessarily position x? So here, like a derivative with respect to k momentum is like a position operator. So here polarization is like, in classical system, it is just a linear function of x. So can we, it might be that the corner charge in three-dimensional system is related to the higher multipoles. So can we do the same thing to compute multiple moment of crystal? But then, unfortunately, this kind of trial all failed. Like the second derivative with respect to the momentum. So this seems to be just, for example, x times y. But turns out this quantity is gauge dependent. So if you change the choice of the phase of this Bloch wave function, this quantity changes not only by integer, but also by some random number. So this cannot be a topological invariant for us. And this way, people try many ways, but fail to develop very systematic formula for multiple moment. So what we want to do is to develop some formula for a higher order multiple moment. And so this is the goal of my research. So we want to give a generalized formula for multiple moment, like a defined formulas that characterizes the trivial phases of matter, not only the polarization, but also quadrupole moment or octupole moment. And I want to understand the relation between this bulk quantity to corner or hinge charges. And given this knowledge, I want to propose some new material which features fractional charges. And it turned out that, according to our theory, the best example of insulator, trivial insulator with corner charges table salt, like NS sodium chloride. And we predict that cubic crystal of sodium chloride, the charge localized to corner is 1/8 of unit charge. So that's the bottom line of my talk. Okay. And okay, so we do something similar. So we just try to generalize this story, bulk polarization to corner charge. We want to generalize this idea to three-dimensional material and the relation between bulk octupole moment and the corner charge. But we have something, some limitation to this kind of prediction. For example, when you compute classical polarization of the bulk, one-dimensional polarization, here I'm taking this unit cell. So blue is here, red is here, and distance between them is d. Then I compute polarization, position times charge, I get this number. But this calculation is ambiguous. Like if you change choice of unit cell this way, now I have red here, blue here, the same arrangement of charges, but I chose my way of viewing it. Then the answer I get is now changed to E times D over A minus E. So this example shows that integer part of surface charge cannot be predicted from the bulk. You can understand the same thing from the surface perspective. You have some material, you have bulk, and you predict corner charge or edge charge. But after predicting it, you can freely bring in additional charge from the outside. Then the sign of the charge can be flipped, or the integer part can be freely modified. So there's of course some limitation to what you can predict from the bulk perspective. So this bulk boundary correspondence is not completely not complete in the sense that it cannot predict integer part of your edge charge, but it can still predict fractional part. So for example, if this bulk polarization is 1/2, then you expect that the charge is always comes with integer plus 1/2. So that's what you can predict. Also, there's like a symmetry quantization. Like for example, under inversion symmetry, polarization flips sign, P becomes minus P under inversion. So it looks like, P goes minus P implies that P equals 0. But as I said, we have integer ambiguity. So, it can be 1/2. So this is the reason why we have this like 1/2 fractional charge on corner of invariant symmetric insulator. And then people understand a very simple understanding of this fractional charge, which is called filling anomaly. So this is called anomaly, but it's not really deep. It's very simple. So suppose let's assume that we have translation symmetry and inversion symmetry. Okay, but translation symmetry is broken by the presence of surface. So you assume a point group symmetry, inversion symmetry. Okay, but if you impose this inversion symmetry, then the total charge in this system cannot be charge neutral. Like, okay, so this red is plus E, this blue is minus E charge. Okay, if you really impose this symmetry, then there's no way for us to modify charge distribution in the system in such a way that this system becomes charge neutral, right? If you move this blue in this direction, this blue also have to move this direction. So there's no way for us to neutralize the charge in this system. So this kind of phenomena, you cannot simultaneously satisfy charge neutrality and point group symmetry. This is called like a filling anomaly recently in condensed matter systems. And when this occurs, we know there must be corner charge or edge charge localized to corners, because in the bulk, plus and minus cancel each other, and it is charge neutral. But we know that we have extra charge in the system. Extra charge can only go to the edge of the system. So, and because we have inversion symmetry, you divide it by 2. So that is why we have this 1/2 charge at the edge. So this is a kind of simplest example, a simplest understanding of edge charge in these one-dimensional systems. And basically, we do the same thing in higher dimensional systems. But before doing that, I want to explain the more precise definition of edge charge or corner charge. So because of the U1 symmetry of the system, we have a net current, and the zeroth component is the charge density operator. And you take expectation value of this charge density operator. So that gives us some microscopic charge distribution in the bulk. But this is highly oscillating, I say, in ionic crystal like sodium chloride. It is very positive at the sodium position, and chloride position is very negative, and it's highly oscillating. But that's like oscillating at microscopic, like angstrom length scale, right? So in order to see something more, I don't know, from a more daily length scale, like 1 meter length scale, we perform some coarse graining. So I take some Gaussian function and I perform some Gaussian convolution. This is like a coarse graining procedure. Then after doing so, I see that in the bulk, the charge distribution is almost 0. Charge density is 0. And remaining charge is localized to corners. So this is, after I get this coarse graining procedure, Gaussian convolution. Then I define corner charge to be the special integral of this, some peaks around the corner. So this is the definition of corner charge. And basically, I do this. I do this to three-dimensional crystals. So let me, yeah. So for example, I have a sodium chloride crystal.
I'm sorry. Can I ask you a question?
Sure.
When you did your convolution, so it seemed that what happens before and after the convolution seems different, but of course, I mean, it can't be, right? So in the
before and after convolution, so these are So this is a microscopic charge distribution.
Yeah.
What I'm proposing is, because this is like an angstrom length scale, let us look at it slightly like a further, rough length scale. So that is done by this convolution. So I can set this parameter lambda. So this is this determines the coarse graining length scale. So say in this case I'm choosing it to be 3A. So I kind of take special average of charges in this 3A length scale, and that gives us this, charge distribution.
This is, what you're saying here is that on the boundary, since there's nothing on the other side, then the net charge must be non-zero. While once you integrate in the bulk, you always get more or less zero because you're getting an even number of stuff.
Right. So in the bulk, charges are balanced. So if you take special average, you always get zero. But on the boundary, you are missing the pair to neutralize it. So that's why you have excess charges. So that's the reason why I have this kind of peak here.
Okay, I understand. Thank you.
Oh, thanks for clarifying question. Is there any other questions? Yeah, I'm glad that I'm running out of time. Like I thought, my talk can be done in 10 minutes, but great. Yeah, because I'm running out of time. Let me just give you the simplest understanding of 1/8 corner charge of sodium chloride. So in this system, I have positive charge and negative charge, and it is arranged periodically. So the simplest understanding of corner charge of sodium chloride is the following. So in this setting, I choose the system in such a way that it is rotation symmetric. So you have not perfect continuous rotation symmetry, but it is called octahedron symmetry. So this corner and this corner and this corner and this corner, all corners are equivalent, symmetry equivalent. So you have 4-fold rotation symmetry and 3-fold rotation symmetry that relate corners. So all corners must support the same amount of charge. Then you count the total number of particles or total number of electric charge in this system. It turns out that the total charge in this system is not zero. In this setting, if you impose the complete octahedron symmetry, then the charge is actually plus E. So you have excess charge plus E, and you divide it by the number of corners. So that's the reason why we have 1/8 corner charge in this system. But if we explain this way, you might wonder, okay, in order to observe this effect, we have to really prepare a perfect cubic symmetry that in which all corners are symmetry equivalent. But I would say that's not the case. And for example, in this setting, I have one corner occupied by sodium ion, and the other corner occupied by chloride ion. In that case, it is natural to expect that one corner supports 1/8 charge, and the other corner supports -1/8 charge. And this is what I literally computed the charge distribution in the system. So even if we break the rotation symmetry of the system, octahedron symmetry of the system, the corner charge is the local property of this corner. So as long as the local charge ionic distribution of this corner is unchanged, we get the same answer. Maybe the simplest way of understanding it might be just this kind of coupled wire argument. So I explained that polarization implies edge charge. So plus E, minus E, plus E, minus E, this kind of arrangement of charge in one dimension implies charge at the end, which is plus E, 1/2 or minus 1/2, depending on the termination you have, right? I want to understand this 3D system using this simplest case of 1D sodium chloride. So let me go to 2 dimension. So in 2 dimension, I decompose this system into the arrangement of 1D wires. So I looked at this column. This is plus E, minus E, plus E, minus E. So this is exactly this situation, right? So I use this knowledge to make it minus 1/2 charge and plus 1/2 charge. This this 1D line comes from this line. I go to the second column and I do this understanding and make it this 1D line with 1/2 charge. And now this edge charges of this 1D system can be seen as new 1D system with alternating sign. So this predicts 1/4 charge at the corner of this 2D system. And I repeat this argument to decompose this 3D system into the layers of 2D systems. And this have 1D edges with alternating charges with 1/4 of charges now. So that predicts 1/8 charge at the corner of the system.
So the fact that you have the charges only at the corner, so only at points, is this the reason why you don't have problems with gauge invariance that you were talking about before? I mean,
oh yeah, yeah. So actually, the gauge invariance I was talking about is more about like a surface decoration. So in this context, gauge invariance of the bulk wave function actually correspond to the amount of things we can change by looking at the boundary and bringing in something outside. Like the 1D problem, here I said, we can change the amount of edge charge by bringing in new charges from outside. That changes the integer part. And the integer ambiguity was what we had in the this kind of formula for bulk polarization. So this is a formula for bulk polarization, but this one has integer ambiguity. Like you change the wave function by I theta, and this theta is assumed to be some function periodic in momentum space. So you see some like a winding number that it gives you integer ambiguity. So like there's a correspondence between the bulk wave function ambiguity and surface decoration. And here, the simplest understanding of the absence of such kind of ambiguity for fractional corner charge is that you cannot really remove the 1/8 part of the corner charge. You can try to remove it by attaching to it some 2D system with corner charge or 1D system with random polarization. But as long as you impose the octahedron symmetry, we know that it is not possible to remove the 1/8 charge. So for example, this polarization is quantized to 1/2, or corner charge of this 2D system is quantized to 1/4 of the unit charge. So what you can predict from the surface perspective, from the bulk perspective is only the modulo 1/4. So this part can be modified freely from the attaching or decoration of the surface, but this part is robust. Actually, this is the end of my talk. And okay, the last thing I want to mention is that whether we can measure this effect. So I just computed the electric field created by ions in the system. You see? So I just computed the Coulomb force from this corner as a function of this distance d. What I found is that if the distance is very short, like 0.0, so this is like in the unit of 1 ionic distance. So this is like an Ångström length scale. Then you see that the coefficient is E squared over D squared. So this implies that at the corner I have unit charge, like a sodium ion. However, as I get far away from the corner, then I start to see something coarse-grained. And that was the definition of corner charge, right? So I smoothly cross over into the corner charge region. So that is 1/8, so E squared over 8 D squared. So this is the signature of fractional corner charge of this, localized to the corner. And as I go further, then I start to see everything in the material. So as a whole, I assume that this system is charge neutral. So there's no E squared over D squared term. So this goes to some random number. But in this region, at least in this region, I can see the signature of corner charge, fractional corner charge. So that was my proposal. Thanks. So yeah. So the summary wise. So today I talk about the comparison between topological phase and topological phases. In topological phases, we have modes like zero mode or gapless modes lives on the boundary that is related to anomaly of the system. And but we can see similar correspondence between bulk and boundary, even in trivial phases, like ionic crystal. The wave function is completely trivial. Plus ion, minus ion. That's like a product state, right? So it's a trivial insulator. But still, nonetheless, you may still see some like interesting signature on the boundary, on the corner or boundary. And that was related to filling anomaly in quantum systems. Thank you so much.
Okay, thank you very much for the talk.
Thanks a lot.
I learned a lot of things personally.
Oh, great, thank you.